In this video, let us discuss about two very important problems related to classical mechanics, of which the first one, that is, we have to use Rauthian function method to find out the equation of motion in case of Kepler's problem, that is, in case of planetary motion, obviously for the non-ignorable coordinates r. Now I hope you all know what is the definition of cyclic coordinate or ignorable coordinate. So here we are going to discuss about the equation of motion for the non-ignorable coordinate, that is r. Now as you can see in this diagram, I have considered a certain particle of mass m is located at a distance r with respect to origin. That means if you join O and P, then that will be denoted by some radius vector r. So obviously there is an arrowhead directed towards O, that means the particle is moving under the influence of some attractive force. So we can say that this particle of mass m is acting towards the origin by means of inverse square law. Obviously it should maintain the inverse square law where f is proportional to 1 by r square, and definitely we can write f is equivalent to, that is the acting force is equivalent to, minus m mu by r square, where mu is some constant. Now if we consider r comma theta be the coordinate of the point or coordinate of the particle, better to say, in terms of polar coordinate system at any instant t, then kinetic energy of the particle will be given by t, that is half of mv square, and potential energy function, that is v, will be given by minus of integration f r dr. We know this from definition. Now because you are considering the polar coordinate system, so that's why you can say the velocity can be decomposed into two parts. One is radial velocity, that is r dot, and the second one is cross radial velocity, that is r theta dot. So that's why half of mv square can be modified as half of m into r dot square plus r square theta dot square. So this is equation number 1. Now obviously for function v, we can consider the value of f what we have described earlier, that is minus m mu by r square. So simple integration will give you minus m mu by r. Now let us consider the Lagrangian. Obviously r comma theta is the generalized coordinate in this case, so Lagrangian will be given by t minus v, that is half of m multiplied by r dot square plus r square theta dot square plus m mu by r, because already we have obtained the values of t and v by means of equation 1 and 2. So say this is equation number 3, and as you can see, theta is the ignorable coordinate in this case, and we all know this is also another standard result, that the generalized momenta corresponding to theta will be constant. That means if you consider p theta, which is given by del theta dot of L, that must be a constant. Now if you differentiate partially this expression with respect to theta dot, then you can easily find out the expression for p theta, which is nothing but m r square theta dot. From here you can obtain this expression. So say this is some constant, that is c. So from here we can find out the value of theta dot, which is c by m r square. Now it's time to construct the Rauthian function r. As we all know, r can be considered as L minus c theta dot. Already we have obtained the expression of theta dot, we have obtained the expression for L. So simply put these values. Now what is our next task? You can easily understand theta dot should be replaced by means of c by m r square in this expression as well as in this part. So remember the structure, half of m r dot square plus r square, theta dot square will be modified as c square by m square r to the power 4 plus m mu by r, keep this one intact, minus c theta dot, that is c into c by m r square, that will be modified as c square by m r square. So we have used these values here just to simplify this expression. Now after simplification you will get what? Half of m r dot square plus c square, r square will be cancelled, so m square r square plus m mu by r minus c square by m r square. So just consider the first expression, second expression after multiplying it by m, as well as you can consider the last term in the third position and the third term in the last position. So if you take half of m common from the first three terms, or better to say from the first two terms after modification, then you can easily obtain r dot square minus c square by m square r square, and the last term remains intact, m mu by r. So this is equation number 6. Now from this equation 6 you can easily find out del r of capital R, del r dot of capital R, and if you differentiate it further with respect to t, then you can also obtain ddt of del r dot of capital R. So actually we have differentiated partially equation number 6 with respect to small r and small r dot to obtain all these values. Now here you can see I have put these values within a box so that you can easily understand this one, because we are going to implement this result later on. And finally we can use the corresponding results in the Rauthian equation for non-ignorable coordinate theta. As mentioned earlier, here theta is the ignorable coordinate, so obviously non-ignorable coordinate will be r. Okay, so in this case ddt of del r dot of capital R minus del r of capital R should be equal to 0. Now here also you can see this equation is very much similar to the Lagrange's equation of motion, as if you have replaced L by R. So simply we have to put all these values in this equation, and obviously after putting all these values you can see mr dot dot will be the first expression, del r of capital R will be this expression. So combining all this you will get required equation number 8, which is nothing but a second order differential equation, and if necessary you can also integrate this one. And also you can observe this particular equation contains only r, so you can say this is the required equation of motion in case of planetary motion, or in other words you can say this is the particular equation of motion in case of Kepler's problem, whatever you have constructed by means of Rauthian function method. So this is a very important question. I hope you can understand this solution, so you can easily prepare this one for your examination. Now moving on to the second one, we can consider the concept of geodesic. Now before going through the equation of geodesic for a spherical surface, first I have given two notes so that you can easily understand what is the meaning of geodesic. Actually, whenever you are considering a geodesic, it is nothing but a line segment that represents the shortest path between any 2 points when the path is restricted by means of some certain surface. It can be spherical or some other surface also. So actually whenever you want to find out the shortest distance on a curved surface, then definitely you need to take the help of geodesic. So that's why I have given this note 1. And also geodesics of a spherical surface are always great circle. Now I hope you know from graduation that what is the meaning of great circle. Whenever the radius of the sphere and the radius of any circular section within that sphere becomes identical, then that circle will be considered as great circle. So that's why we can say the circles whose centers lie on the center of the sphere can be considered as a great circle. So to solve this one, you can see I have started with the spherical polar coordinate system r theta pi. Now obviously from elementary differential calculus we can say ds2 can be written as r square within bracket d theta square plus sine square theta d phi 2, so that ds can be written as the positive square root of this expression. And if possible, let us assume there exist any two specific points p1 and p2, and we want to find out the integral by means of a path joining these 2 points. And since s is the arc length, and if we consider between p1 and p2 the arc length is very small, so we can find out I by means of using this result. So simply put this expression here, because already you know what is the value of ds. Now consider this particular expression as f. So I have mentioned this one as f, and also you can see I have written another criteria phi dot, that is equals to dd theta of phi. Now in order to get the extreme values for the integral I, we can use this Lagrange's equation of motion, that is nothing but equation number 2. Now you can obtain from this particular equation 1 del f del phi is equal to 0, because there is nothing related to phi, but del f del phi dot, this can be obtained as del phi dot of this entire expression. Now simply you can differentiate this entire expression so that you can simplify the structure to obtain this particular expression, r into phi dot sine square theta whole divided by 1 plus sine square theta multiplied by phi dot square whole to the power half. So if we have obtained this particular expression, so this can be put in this expression also. That means dd theta of this particular structure should be equal to 0, because as mentioned earlier del f del phi is already 0. So simply put these values equal to 0. So technically dd theta of this particular structure is equal to 0, because we have eliminated r. Why? Because r is constant. Now simple integration will give you this particular portion is equals to some constant c. This is nothing but is constant. So phi dot sine square theta can be written as c into this entire portion. Now just squaring both sides, and after simple calculation you can easily find out the expression corresponding to phi dot square, and from there on you can also find out the expression corresponding to phi dot as shown here. I have given already the detailed solution of this expression, that's why I am not explaining this one, because if you go through this calculation you can easily understand. So after obtaining the expression for phi dot like this, you can modify this expression. Here you can observe one particular thing, c square can be visualized as c square into 1, so that you can write c square into sin square theta plus cos square theta, and obviously later on you can see 1 sin square theta by sin square theta will be 1, cos square theta by sin square theta will be cot square theta. So phi dot will be equal to c into cosec square theta, because you can take it in the numerator portion by considering the reciprocal, and 1 minus c square from this particular portion minus c square cot square theta whole to the power half. Now from again this particular expression you can take c square common within square root, so that c will come outside of this expression, c will be cancelled. For simplicity you can consider this particular structure is equal to k1 square. Now simply integrate this one, and that's why after integration you will get this type of structure. Again we have taken k1 common from this expression, so after integration you can see, for integration we have taken this substitution, we can obtain this type of structure. Here alpha is a suitable constant. So after simplification you will be able to find out the exact value of phi, and obviously here we have taken another modified constant, that is k, which is nothing but the reciprocal of k1. So after simplification I hope you can easily obtain equation number 5. Now converting it into the spherical polar coordinate system by using the formal expressions, x is equals to r sin theta cos phi, y is equals to r sin theta sin phi, and z equals to r cos theta, we can say cos theta is equals to z by r, so that we can put this expression in equation number 5, and after simplification we can obtain kz is equals to r of this entire expression. Now using the formula for compound angle you can split this one, so that you can separate r sin theta cos phi multiplied by sin alpha, but actually this is x, as you can see from equation 6. Similarly from the next part r sin theta sin phi cos alpha will appear, but this part is nothing but y. So in this way you can obtain zk is equals to x sin alpha minus y cos alpha. But obviously you must not forget what is the value of r square is nothing but x square plus y square plus z square. So thus we have obtained a certain equation, that is equation number 7. Actually it represents a certain plane which is passing through the origin, and whenever it cuts the spherical surface into a great circle, that will give you the required equation of the geodesic. So in this way you can easily find out the geodesic corresponding to a spherical surface, and all these languages are formal languages, and entire calculation I have given to you, and I hope you can easily understand the calculation also. So please go through these problems, because these problems are very important from examination point of view, and I hope you can easily prepare these problems for your examination again. And thank you for watching, and if you have any doubt then you can ask me through the comment box. Thank you.